Okay, so maybe we can start now. Hello, everyone. Today I'm going to talk about our ongoing project called tripartite entanglement of the topological basis. It is under the supervision of Shinsei and also work with Jonah.
Can we try and adjust the microphone a little? Is anyone else having trouble hearing?
Sorry.
No, it's just a little muffled for some reason.
Let's see. Let me try to make it louder. Sorry.
It might just be me. In which case, don't worry about it.
I think it's a little muffled, but I don't know. Sometimes that's just Zoom.
So where can I change that setting? Like,
I think I hear well. I think it's better now.
Okay, thank you. Okay, so yeah, then let me continue on that. Okay, so in the first part, I'm going to talk about.
Sorry, Yuhan, I think your screen stopped sharing.
I see. Okay, here we go. Yeah, so in the first part, I'm going to talk about our motivation. I'm going to give a brief introduction to the boundary conformal field theory and talk about why the boundary conformal theory is related to the ground state of the gappy topological order phase. Okay, then let's start from the boundary CFT. So in the string theory class, we learned a little bit about the open string theory. Let's take the Newman boundary condition as an example. So in that case, we can write the boundary condition in this form. And because of that, we actually only have the half of the degree of freedom in the system because we need to make this identification. But equivalently, by using the so-called open-closed duality, we can also study the same problem in the closed string theory setting. So now we only need to impose the Newman boundary condition on the state B, which we call that to be the so-called boundary state. And in the free bosons conformal field theory, we can find the solution to the boundary state quite easily. And notice that because here the summation goes from 1 to infinity, so we actually have the solution here to be a coherent state because we can write that like to something like this, that we have a pair of the Asian operators. And then by some manipulation, we can also bring the solution to the boundary state to the more general form of the so-called Ishi-Bashi state, which is on the second line here. So the Ishi-Bashi state can be useful when we want to talk about the rational conformal field theory. Okay, because eventually we want to study the fermionic system, so it is more useful to us to talk about the boundary CFT in the free fermion setting. The free fermion boundary CFT consists of two chiral fermions. So we can see that we have one left moving copy, and the other is the right moving copy. And we can kind of view that in the figure here. That here we have the first copy, and here we have the second copy, and they have the opposite chirality. And in a similar way, we can also write down the boundary condition for the free fermion BCFT. And probably you notice that here it is a little bit different, that we have this factor I that we don't have in the free bosons case. So why is it that here we have this factor? It is actually comes from the fact that the conformal weight for the free fermion is equal to 1/2. So it actually comes from this factor. And then by doing the Fourier transformation, we can bring that to the boundary condition in the second line. And finally, here gives the solution to the boundary state in the fermionic system. And one thing to notice is that here the vacuum state 0 is kind of like the half-field Fermi C. So even that here we don't have the dagger, but it actually creates the hole. So we can say that it is still somehow in the general form of the coherent state like this. Okay, so now we talk about the boundary safety for the free bosons and the free fermion. Then the next question to ask is how the boundary state can be related to the topological state that we are interested in. So here we are going to use the simple example of the integer quantum Hall effect to illustrate the idea. So the edge theory of the integer quantum Hall effect is the two chiral free fermions, which is actually the same system that we talked about in the previous slide. So here we basically follow the treatment in this PRL paper by Qi and his companies. So by taking the gated Hamiltonian of the integer quantum Hall effect to be this form, we can find its ground state easily. So here is the ground state of the above Hamiltonian, because it is a free fermion system, the ground state is always easy to find. And so here comes the important point that we have this vector here. So by making the identification, because here we can see that the C is the left moving part and the D is the right moving part. So by making the identification that CK dagger corresponds to a chi left, K, and the DK corresponds to a chi right, K. We can find that these two expressions are actually the same. So it is the important point here that we finally come to the following relation, that the ground state of a gapped topological phase can be related to the boundary state up to some regulator. So here, when talk about the regulator, I talk about this part. Yeah, so basically they are the same.
Hi, Yuhan.
Hi.
In the interaction term here, should it be CK dagger DK plus remission conjugate, the couple left and right?
You mean this term that
Yeah.
yeah, so I think in their paper, this term is only the mass term that generate the gap, and I think they haven't talked about the interaction in their model.
I think it should be C dagger D and D dagger C.
Yeah.
Yeah, that's what I was asking.
Like this. Yeah.
Yeah, and then, yeah, the state looks right for that, yeah.
Yeah, that's right. So it is like this to couple the two copies. Yeah. Sorry for that. It is a typo.
No problem, thanks.
Okay, then okay, so in the last slide, we only talk about the simple example of the integer and how it does, but in a more general setting, that we can also find the correspondence between the transcendent theory in the bulk and the rational conformal field theory on the boundary. So here I mainly refer to this paper that so because on the boundary we have the rational conformal field theory, so we have some finite number of the primary fields. So here A is the label for the different primary fields, and here H is the so-called issue state that I mentioned before. And then here psi is some coefficients. So we can use the similar trick to add some regulator here. So finally, we can see that the gapped ground state of the topological order system is also related to the boundary state in the rational CFT. And then by using the ground state here, we can also find the and string entropy. So because here we have an L, we can see that the first term is a term that corresponds to the area law. And then for the other terms, because it is only related to the capital D and the DA, so it kind of encodes the topological entropy. So it is the topological term. Okay, so we have finished the introduction to the boundary set T, and the takeaway message from the first part is we can use the boundary set T to study the topological order phase. Okay, so before we move to the second part, is there any question? Okay, so hopefully that the introduction part is clear. Then let's because we want to study the so-called tripartite entanglement, we will need to bring the system into three pieces, not the two pieces that we talked before, which means that we will need to move from the boundary state to the so-called vertex state. And I'm going to define the vertex state in the following. Okay, so the first thing we are going to do is to modify the equation that we have before. So the only thing that we have changed here is bring the sigma to the 2 pi minus sigma, and then in this way, our overlap equation actually looks more natural. Why is it that it is more natural? Because so now that we are talking about a system in the figure A, it is the system that we have two strings like this. So here we have 0 here and pi here. It is the string A. And then for the string A complement, we have 0 here and 2 pi here. So so this overlap equation basically says that we will need to do the following identification, that between the points here. Okay, so the benefits for this modification is that it can make it easier to generalize to the case that we have 3 copies of the Carroll fermions, which is the case in the figure B. Okay, so how does that work? Now that we have 3 strings, so 0 to 2 pi, because it is closed string. So now from the first equation, suppose that here is my A and here is my B. So you need to identify this part. And then from the second equation, we need to identify this part. And finally, this part. And a different way to understand that is to think about that we are actually grouped in the 3 cylinders. And suppose we have the first cylinder, the second, and make it bigger, the second and the third. So by gluing this part to this part and this part to this part, and finally here we are going to have something like this. So finally, after the gluing, we are going to have this junction, something like this. Okay, so now that we have the overlap equation for the vertex state, we can somehow try to find a solution to that. So here we give the solution to the vertex state with the coefficient matrix to be the capital K. So because our overlap equation is more complicated than the previous case, the form for the matrix K can also be more complicated. But the same feature is that here the vertex state is still the coherent state, or so-called Gaussian state, because we still have to add dagger here. So somehow the solution here still share the same feature as the boundary state we had before. Okay, so now that it comes to the question that whether the vertex state that we find in the last slide is also related to the topological space. And here we make the conjecture that this relation still holds for the vertex state. And the only thing that we need to modify is the Hamiltonian in the regulator, because now we have 3 chiral copies. So yeah, so it is the only difference. And in the following, we can see some hints of the support from the numerics that hopefully it is correct. So here is the conjecture that we are making here. Okay, so so before I go to part 3 and part 4, I would like to pause for a second and talk about why the tripartite entanglement is interesting to study. So I think our first answer is that the tripartition makes it natural to study the entanglement negativity in the topological order base. And I'm going to introduce the entanglement negativity in the part 3. Basically, in order to compute the entanglement negativity, we will need to break our system, say, into 3 different pieces, A and B and C. So the tripartition makes it natural to compute the entanglement negativity. And the second interesting point is about the corner that appears here. So it is possible that the corner at this intersection point may bring some singular behavior, and it is actually talked about a little bit in this paper by Gross and Jalicki. And the third point is probably more relevant to the people in the string theory. It's because the vertex state actually shares the same overlap equation with the interacting string theory, or the so-called string field theory. So hopefully by knowing the solution to the vertex state, we can also study the entanglement in the string theory. And I'm going to talk about this briefly in part 4. Okay, so now we are going to talk about the numerical results in the tripartite entanglement. Yeah, so before we define the entanglement negativity, we will first need to define what is the partial transpose. So now that I break my lattice into 3 pieces, and after tracing out the pieces on the right hand side, we can get the reduced density matrix on the part of A union B. So the partial transpose in the bosonic system is quite natural. If you just stare at this equation, the only thing that the partial transpose does is that it is changing the index of I and K. So one may wonder that whether we can still use the same definition for the system of fermions, but however, the answer is no, because it doesn't satisfy some property that the partial transpose should satisfy, because like the so-called additive property, so it only satisfies for the bosonic partial transpose case, but not in the fermion case. So you need to define the partial transpose for the fermion using a different way. And if you are interested in the details, you can look at these 2 papers. So the answer is that to define the fermionic partial transpose, we will need to insert this vector that I to the power k1 here for the row T A, and which can satisfy some certain conditions in this definition. Okay, so we take that and we can use the partial transpose to define the entanglement negativity. So why is it that you need to use the entanglement negativity other than the entanglement entropy? Because people find that if we study the mixed state, the entanglement entropy will include both the classical and the quantum contribution. But for the entanglement negativity, it is only going to have the quantum contribution. So by knowing the entanglement negativity, it can provide us with more information about the system we are interested in. And besides the entanglement entropy and the negativity, we can also study the spectrums. So I think it is a little bit nickel here, but by so for the Gaussian state, we can use the so-called covariance matches method, and the entanglement spectrum and the negativity spectrum are related to this gamma matrix, but that is a little bit detail. So finally, now that we have all the tools that we need, we can apply that method to some concrete lattice model, which is the model for the chain insulator. So here is the famous Hamiltonian for the chain insulator, and notice that here we have a parameter U. So the chain number equals to 1 when U falls in the region from 0 to 2, and so because the parameter that U equals to 1 is deep in the topological phase, so it is the parameter that we are interested in, and it is the parameter that we are going to use to compare to the result that we get from the vertex state in the boundary conformal field theory. Okay, so here shows the results. So the first one is the entanglement entropy, and we can see that like here when U equals to 2 and -2, we have some kinks. And the reason is that when U equals to 2, 0, or -2, we have the phase transition. So that is why that we have the kinks at this point. And then furthermore, so the second figure shows the entanglement spectrum, and the third figure shows the negativity spectrum. We can see that when U equals to 2, basically at these 2 points, that the spectrum here is not continuous, which gives the hint that we have the phase transition at this point. Yeah, and as I mentioned before, we are actually interested in the U equals to 1 case. So we can focus on the third figure, which is the negativity spectrum. And if we only look at this part, which is the flow line spectrum, we can see that it roughly has the equal spacing that we are going to talk about later. Equal spacing. Okay, and because we also need to compute the partial transpose, we can also have a look at the spectrum of the partial transpose rho A. So in the first 3 figures, we have the parameter being U equals to 1, which are in the topological phase, and in the last one, we have U equals to 3, which is in the trivial phase. Okay, so let's first focus on the first one, because after the partial transpose, the rho TA is not necessary to be a Hermitian matrix, and that is why that we can actually have this spectrum on this complex plane. So in the first figure, we take this eigenvalue that probably be a little bit hard to see this point. And on the right panel, we plot its corresponding eigenvector. So the geometry is like here we have part A, and here we have B. And the A union B complement is kind of like on the right. So we can see that this eigenvector is actually localized at the corner or the intersection points because it is basically here. So it is localized at the corner. Then we come to the second figure that we choose an eigenvalue that is on the middle part of this figure, which is here. Yeah, and similarly, it is A and B. We can see that this eigenfunction is localized at the boundary between the system A and B. So it is localized at the boundary. Then in the third figure, the point that we choose is here. So it is at -1. And we found that at this point, the eigenfunction is distributed in the bulk. So it is not that interesting. It is in the bulk. Then finally, when it comes to the parameter u equals to 3, which is in the trivial phase, that we take the value here, and we see that, so here is the A union B complement. And we see that this eigenfunction is localized at the boundary between the A union B and its complement. So even that it is still localized at the boundary, it is still different from the second case. So we can see some interesting feature in the spectrum of rho TA. Okay, then after showing the numerical result, we can finally come back to our conjecture before, that whether it is really true that the ground state is related to the vertex state. So at this point, we can say that we have some hints or the supports from our numerics. So like we can see that here that the spectrum has the behavior of equal spacing, which is actually a CFT signature, and the degeneracy for the negativity spectrum also match. So here is the result from the chain insulator, and then on the right hand side, it is the result from the vertex state. But one thing that makes them slightly different is that from the result from the vertex state, we can kind of see that they comes into a group. So I will put a question mark here, that why is it that it is not the same? And the second thing that we compare is the spectrum for the partial transpose. So again, the figure on the left is from the ground state of chain insulator, and the figure on the right is from the vertex state. We can also see that they have the similar shape. So we say that we have some hints from the numerics, and we're going to look into that further in our future work. Okay, and we also show the partial transpose spectrum from the vertex state. So now the system is somehow like this, and we have traced out one of the string. So suppose that this part has been traced out, and these are our whole system. So in the first one, we take the eigenvalue here, and in the second one, we take that in the middle. We can see that in the both cases, the eigenfunctions are localized at the boundary between the first string and the second one. And then in the last case, we take the eigenvalue to be at point 1, which is basically the same as choosing the value to be at -1. And we can see that it is kind of distributed in the bulk. So we can say that the first two at the boundary and the third one is in the bulk, which is quite similar to the result that we can get from the training paper before. Okay, so we finished the part 3, and in the last part, I'm going to talk about briefly the human function method and the interesting Wheaton's vertex. The human function method is a different way that we can get the solution for the vertex state. Yeah, and because I'm actually not so familiar with the string theory, so if anything here is not so accurate, you are welcome to point that out. Okay, so from my personal understanding, the string field theory was proposed as an interacting string theory, which is also gauge invariant. We can see that the action for the string field theory has two different pieces. The first piece is a kinetic term, and the second piece is the interacting term. And we can see that our vertex state actually appear in this interacting term. And it is, I think it is first mentioned in this famous paper by Wheaton. And we can take the definition that the vertex state is defined to satisfy the following equation. So the H1, H2, and H3 are three different conformal map, and then here the capital A, B, C are the so here the A, B, and C are the states in the string field. So we can try to convince ourselves that the solution for the vertex state actually takes this form, and you can find that these T's are basically our Prometheus, like 1/2 and a dagger. some coefficient A dagger. So yeah, and also for the other pieces. So they are basically the same as what we have before. And the interesting thing to notice is that here we have the so-called we have the 2-point functions in the so-called Newman coefficients. Why is it that? Like, looking back to the equation that we want to satisfy. So on the left-hand side, it is some correlator. So suppose that it is a 4-point function or the 6-point function. We can always use the Weeks theorem to finally bring that to the product of the 2-point function. So by using that logic, and maybe by trying some simple example, you can convince yourself that the vertex here actually satisfy this equation, and it is basically the 2-point function for partial x. Yeah. After making some conformal transformation. Okay, so we see that every choice of the conformal transformation can give a different vertex state. But our motivation is that we want the interacting string theory to be gauged invariant. So in order to have the BRST symmetry, we will need to also we will need to impose some constraint on the conformal transformation. So here we have t squared, and on the second we have t, and we require that t cube equals to 1. So somehow that it is cyclic. Okay, so now that we come to the famous Wheaton's vertex, so we can make this following choice, and we are going to see that it is quite interesting. Why? Because it can map an open string in the region that tau is greater than 0 to 1/3 of the unit circle. So yeah, so here we can see that it actually tends to infinity, and here is the boundary for that when tau equals to 0. So by this conformal transformation, we can actually bring this region to this part, which is 1/3 of the unit circle. And the boundary here actually becomes the boundary for this part. Okay, and because he also choose t to a 2π/3 rotation, so we can kind of think that it can bring the second copy to here, and it can bring the third copy here. Yeah, so finally we have this picture, which is actually the same as what we want. And by looking at this mapping, we can see that it actually satisfies the same overlap equation. But the only difference is that because here we only talk about the open string. So here we have pi equals we have pi minus sigma, not the 2 pi minus sigma that we have before. Yeah, but the form for the overlap equation is very similar. Okay, and then so we can see that even that we can say that we somehow have the solution for the vertex state from the string field theory, because that we actually need to compute a lot of intervals and some other math. So finding the actual value for the Newman coefficient is actually not that trivial. But thankfully, in these two papers by Gross and Javicki, they gave the numerical form for the Newman coefficients that we need to use, and then using the Newman coefficients that they have in their paper, we can also try to compute the entanglement entropy, the negativity, and their spectrums. So we can see that the negativity spectrum here has a nice equal spacing that is a little bit different to the spectrum that we have here. Yeah, and we also compute the spectrum of the partial transpose, but we found that in this case it is not quite the same because we miss the eigenvalues that in the middle. So now we don't have something here. So here we have to choose two different values for the regulator, but we have shown that no matter how we tune the value, we cannot have that eigenvalues that are at the middle. And but we think that it is different because here we are actually using the solution for the open string field theory and also for the real fermion. But eventually we want to find the vertex state for the closed string field theory and for the complex fermion. So if you happen to know any paper that talks about that, please let me know. And it is interesting to find the behavior for the vertex state in that case. Okay, so it is the last slide of my talk. So the next things that we want to study include the solution for the closed string field theory that I mentioned before, and because that in the numerics we only talk about the case for the chain insulator, so we actually haven't studied the more interesting about logical order system that can have the particles. So it is also interesting to study that case. And besides, we also want to compute the same quantity from the bulk transcendent theory to see that whether the results computed from the bulk can match them to the vertex state in the boundary safety. Okay. Yeah, so that is the end of my talk, and feel free to ask any question.